Dear students, this is our fifth lecture on organic synthesis, and today we will discuss about basic concepts about asymmetric synthesis. Asymmetric synthesis or selective synthesis is basically very important for the pharmaceutical industry because different types of ionomers or diastereomer, they have different biological activity. So because of the different biological activity of these ionomers or diastereomers, they are used as drugs for different purposes. So sometimes you might have seen that out of the two ionomers, only one ionomer is active as a drug, whereas the other ionomer is either not active or it shows some adverse effects on the body. So that is why asymmetric synthesis or selective synthesis is basically very important for pharmaceutical industry. So through this asymmetric synthesis, basically what we do is that we synthesize a compound through some distinct method which will favor the formation of a particular ionomer or a diastereomer. Either only one ionomer will be formed, only one diastereomer will be formed, or one ionomer will be formed in more amounts. That is, if only one ionomer or diastereomer is formed, we say this is a specific synthesis. And if it is formed in more amount, then we say selective synthesis. So as far as IUPAC definition of the asymmetric synthesis is concerned, according to IUPAC, it is defined as a chemical reaction or a reaction sequence in which one or more new elements of chirality are formed in a substrate molecule and which produces the stereoisomeric products in unequal amounts. And those stereoisomeric products, they will be either ionomers or diastereomers. So this is the exact definition of IUPAC. Similarly, another definition of asymmetric synthesis which is given in journal is that asymmetric synthesis is a reaction in which an achiral unit in a substrate molecule means in a reactant, is converted into a chiral unit in the product, where that unequal amounts of stereomers, they are produced, and stereomers may be ionomers or diastereomers. And if the stereoisomers have opposing configurations at each chiral center, then these are called as ionomers, and if they differ at one or more chiral centers, then these are called as diastereomers. So the asymmetric synthesis example is this is very common example of formation of lactic acid from pyruvic acid. So if you react pyruvic acid with hydrogen in presence of nickel, hydrogenation of this carbonyl compound, carbonyl function group will take place, and this will be reduced to alcohol. So the addition of hydrogen in presence of metal take place in such a way that it will produce two ionomers, either minus lactic acid or plus lactic acid. And if both of these they are produced in equal amounts, we say 50% of this and 50% of this is formed, then the reaction is not asymmetric synthesis. because the condition for the asymmetric synthesis is that any one of the enantiomer, either this or this, should be formed in more amount. So only then this can be called as a enantioselective synthesis or asymmetric synthesis. Now, similarly, if the same reaction is done in presence of yeast, so this we can say is a enzyme catalyzed reaction, then we can see that reduction of pyruvic acid to lactic acid take place to give us only minus lactic acid. So only one enantiomer of the lactic acid is formed. So this we can call as the asymmetric synthesis, or and this is a enantiomer specific synthesis, because here one of the enantiomer is not formed in more amount, but only one enantiomer is formed. When one of the enantiomer or diastereomer is formed in more amount, then this is called as enantioselective synthesis. And when only one enantiomer is formed, then it is called as enantiospecific synthesis. So this is the example of asymmetric synthesis where we are getting an enantiospecific synthesis. Now, what is the criteria for this asymmetric synthesis? So, most important criteria for asymmetric synthesis is that this synthesis should be highly stereoselective, that only one of the stereoisomers should be formed in more amount. Only then that synthesis can be called as the asymmetric synthesis. So this is number one condition for asymmetric synthesis, that synthesis should be highly stereoselective. Now if for the asymmetric synthesis we are using a chiral catalyst, then the amount of catalyst used should be very low. That is, low catalyst loadings, they are preferable, and after the reaction the catalyst must be easily separable from the product. So uh, if we cannot isolate the catalyst in pure form from after the reaction, then that type of chiral catalyst is of less utility in comparison to that catalyst which can be easily separable from the product. So this is the other condition, that the chiral catalyst which we are using for asymmetric synthesis, that should be used in low amounts, and it should be separated very easily from the product. Now, if we are using chiral auxiliary instead of chiral catalyst, then also it should be removable without compromising the new, new stereo center which has been created in the product. And again, this should be recoverable in good yield without racemization, because if chirality of the chiral auxiliary is lost after the reaction, then it cannot be reused. So then this is the third condition which is very important for asymmetric synthesis. And then this chiral catalyst or chiral auxiliary which we are using for asymmetric synthesis, they should be available very readily, and they should be inexpensive. And if these are expensive, chiral auxiliary or chiral catalyst, then our synthesis will be very costly. So it will not be preferred. So these chiral auxiliary or catalyst, they should be inexpensive and they should be readily available. Now, the significance of asymmetric synthesis, which I have also told you earlier, that the pure enantiomers, they are more valuable. As far as before 1940 is concerned, these chiral compounds or optically pure compounds, they were generally obtained by isolation from natural products. or they were the racemic mixture of these compounds, they were resolved through very difficult methods to obtain the pure asymmetric products. Or we use laboratory controlled enzymatic reactions for the synthesis of these optically pure compounds. But the problems in all these three were that these optically pure compounds, they can be formed only in very low yields. Further, the enzymatic reaction, the enzymes are not very stable at high temperature. That is, that was also an issue with using enzymes as catalyst. Then enzymes, they were very costly also. So because of that, these were some drawbacks for the formation of optically pure compounds. And then we have seen that in natural products, chirality is vital to life, and most of the natural or biologically occurring molecules, they have been found to be chiral molecules. And best examples, they are enzymes and receptors. All these enzymes and receptors, they are chiral molecules, and they can act as biological catalyst for the inertia-specific reactions. Now, further, as I've told you, that pure enantiomers, they are more valuable because the pure enantiomers or diastereo isomers, they have different biological activity. For example, thalidomide is used as a drug which has a sedative effect, and it was found that out of these two enantiomers, that is S enantiomer and R enantiomer, only S enantiomer has the sedative effect, whereas R enantiomer does not show any sedative effect, but it has some other activity because it fits to a different enzyme active pocket, whereas as an enantiomer that fits the active site of a specific enzyme which will produce the sedative effect. So this is how you can see that the enantiomerism is very important. So using pure enantiomeric compounds can lead to the formation of different drug molecules. Similarly, in case of non-steroidal anti-inflammatory agent, NSAIDs, which are used as anti-inflammatory agents, there also we have seen only one of the enantiomer has the specific anti-inflammatory activity, whereas other enantiomer is not having that activity. Then the significance again is that it is efficient and sustainable. This enables the synthesis of complex molecules in very efficiently and in a sustainable manner. Then, how this stereoselectivity is achieved in different types of organic function group. So, the two factors which are very important is that presence of prochirality and the stereo element that will influence the stereoselectivity when we are to undertake asymmetric synthesis. So when there is a prochirality present in the molecule, or a stereo element is already present in the molecule, then there is a possibility of formation of one stereoisomer in more amount than the other stereoisomer. So, for example, if we take the case of metal mediated addition of a nucleophile to an aldehyde, so we can have different types of situations where either we can take this example here. This uh, substrate which is being used, carbonyl compound and aldehyde. So here in this aldehyde there is no stereo element present. Neither the stereo element is present in the this metal ligand complex. So when this is treated with chiral reagent, then this will pass through a diastereomeric transition state to give us the product. Whereas when this will be reacted with an achiral reagent, then the stereoselectivity which will be achieved through an enantiomeric transition state, because here this group and this group they are different, and when a nucleophile will add across this carbonyl either through rephase or Si phase in the presence of achiral reagent, then possibility of attack from this side or this side will vary because of the heterotopic nature of the substrate, and this will lead to the formation of different amounts of enantiomers. Then second situation is where this R is having a chiral element present. So this has a stereo element present. So that means the reactant which we are using, aldehyde which we are using is already a chiral. So when another chiral center will be created because of the prochirality present in this molecule, that means the type of product formed will be diastereomers. So here either we use chiral reagent or achiral reagent. In both the cases, we will be passing through diastereomeric transition states, and this will lead to the formation of stereoselective products. Then third situation is where neither this aldehyde is having any stereo center, but the ligand which we are using is having a stereo element present in this. So this ligand which we are using is an optically active ligand which is attached to the metal, and because of this optical activity or stereo element present in this, when we react this in presence of chiral reagent or achiral reagent, then also this will pass through diastereomeric transition state, and we will get a diastereomeric product. Now, the mechanism, as far as mechanism is concerned, in presence of an enantiomeric transition state or diastereomeric transition state, the rate of reaction is different in both the cases. For example, when there is no chiral influence present in the molecule, so there is no stereo element present. This is optically inactive. Metal ligand is optically inactive, and if we are using a achiral reagent, that is optically inactive reagent is being used, that means the reaction will pass through an enantiomeric transition state. And these types of reactions where there is no stereo element present throughout the reaction, so here the rate of reaction will take place at identical rates, and equal amounts of enantiomers they will be formed in presence of achiral reagent. So this you can see, if R is converted into a racemic mixture, this has the same amount of activation energy required as the S enantiomer will require to get changed into racemic product. So rate of reaction of either of the enantiomer to get converted into racemic mixture will be same. So such type of reactions, they are not stereoselective reaction, because the amount of enantiomer formed in each case will be same. Whereas under the presence of chiral influence, what we will do is the reaction will produce enantiomers in unequal amounts, and the transition state involved will be diastereomeric transition state. And we can see over here one of the enantiomer is formed at a different rate in comparison to the other. So as the rate of reaction is different for both the enantiomers, then the formation of the product will also be different. So such type of reactions, they are diastereo selective reactions or enantiomeric reactions. Now, what are the fundamental conditions for asymmetric synthesis? There are two fundamental conditions. One is prochirality. So, prochirality is that any reactant which is achiral reactant, which on some reaction can produce a chiral product. Then such type of substrates, they are called as prochiral substrates, and the phenomenon is called as prochirality. So prochirality will depend on the product formed from a prochiral center, and the product formed will either will be anisotropic or diastereotropic. So if it gives us diastereomers, then it will be diastereotropic, the reactant, and if it gives us an enantiomeric product, then it will be enantiotropic reactant. Similarly, asymmetric induction is that when the element of chirality is present, and this plays an active role in the asymmetric synthesis, and this asymmetric induction can be done either by a chiral reagent, that is called as chiral auxiliary. Also chiral auxiliary solvent is chiral, either catalyst is chiral, or when we do the reaction in circularly polarized light. So either through all these things we can introduce chirality in the formation of products. Now stereospecific reactions. A reaction is said to be stereospecific if out of the various possible products, it gives us only one stereoisomer, either an enantiomer or diastereomer. So a reaction in which stereochemistry of the reactants controls the outcome of the reaction. So in general, one stereoisomer of a certain reactant will produce one stereoisomer of the certain product. Whereas a different stereoisomer of the same reactant will produce a different stereoisomer of the same product. So for example, if you see this reaction in case of aldol condensation, when Z-enolate, which is formed from the reaction of ketone with lithium compound, then this Z-enolate, when this is reacted with any carbonyl compound, we will get the product as syn products. So syn diastereomers, they will be formed, but not the anti-diastereomer. So when this has given us one stereoisomer, has given us the diastereospecific products. So such reactions, they are called as stereospecific reaction. Similarly, if we use E-enolate of the same complex and react with the same aldehyde, we will get the anti product, right? So you can see that different diastereomeric products have been given by different isomers of the same reaction, and such type of reactions they are called as stereo specific reaction. And if diastereomeric product is formed, these are called as diastereo specific reaction. If enantiomers are formed, then these are called as enantiospecific specific reaction. So for example, you have seen in the previous slides that pyruvic acid is converted into lactic acid through a enzymatic reaction. Only one enantiomer is formed. So such type of uh, conversion is called as enantiospecific reaction. Then is stereoselective reaction. Stereoselective reactions, as I have already told you, that if uh, in a reaction the reactant gives us one of the stereoisomer uh, in more yield in comparison to other stereoisomers, then such reactions they are called as stereoselective reactions. So then similarly, if the enantiomers they are formed, this is called as enantioselective. If diastereomers they are formed, then this is called as diastereoselective. So examples, there are so many examples of stereoselective reactions. For example, if we take the case of Wittig reaction, we know that carbonyl compounds in presence of uh, these types of triphenyl phosphine derivatives uh, in presence of base, they are converted into alkenes. So when say this parachloro benzaldehyde was reacted with these two Wittig reagents in presence of butyl lithium, then this part will add to the carbonyl system to give us these types of alkenes. And you can see that there is the possibility of formation of these two diastereomers of these two stereoisomers of this alkene, either Z or E stereoisomer can be formed. And you can see if we are using this catalyst, then 12% of Z is formed, 88% of E is formed. So that means here the E stereoisomer is formed predominantly in comparison to Z isomer. So because of the formation of one of the stereoisomer in more form, in more yield in comparison to the other, so this is an example of stereo selective reaction. Similarly, if we do the lithium aluminum hydride reduction of this ketone, 2-chloro-1-phenyl propane 1-one, when this undergo lithium aluminum hydride reduction, these two types of products they are possible on reduction, and these two diastereoisomers can be formed, and it has been formed that if it is formed three times, this is formed one times. So they are formed in ratio of 3:1. So this diastereoisomer is formed in more amount or is formed more predominantly than this one. So this is again an example of stereoselective reaction. Similarly, hydroboration oxidation of this alkene can lead to the formation of these four stereoisomers through hydroboration oxidation. If we are using this diborane where R is H or R is NBBN, so different amounts of stereoisomers they can be formed. And you can see that here this stereoisomer is formed in more amount in both the cases than the other three. stereoisomers possible. And again, because of the more yield of one of the stereoisomers, it is an example of stereoselective reaction. So this is all about basic concepts of asymmetric synthesis, and these are the references which have been used for preparing this lecture. Thank you very much.